So we'll go ahead and get started here. I'm going to introduce the lead researcher on this project, Sonia Ye, who is a research faculty here at UC Davis. She's going to introduce the team and the project. Take it away.
Thank you, Anthony. And I want to thank everybody for calling in. And today's webinar topic is on future transportation energy use under California's climate goals. And I'm joined by my 3 graduate students, Jacob Tedder, Kate Tickman, and Gauri Shankar Mishra. Before I start, I want to just mention 3 points. One is that we have had a nightmare in version control. So if you already downloaded earlier version of the policy brief or technical brief, I would recommend you to go back to the website and download the newest version. So our apologies. And the second point is that the project is funded by the California Energy Commission's Public Interest Energy Research, or is so-called a PEER program. We have a report coming up that will cover much larger scope of the analysis. But in today's webinar, we'll only cover a portion of it. So if you're interested in this topics that we're not covering in today's webinar, and hopefully you'll become clear when we walk you through the webinar, I would encourage you to download our future report when it comes out. The third point I want to raise is that in this webinar, we really, I want to explain our scope a little bit. That is that we're taking really a consumption-based approach to look at the impacts of California energy, particularly in transportation sector consumption, on water use, and attribute the water use within the state and outside of the state. We're very aware of that. For example, oil and gas production could increase regardless of the changes in consumption, and we have included those scenarios in our report. But the purpose of this webinar is really to show that what could be possible, but it's really not intended to be a projection. So with that, I'm going to start our presentation. And feel free to ask any questions, and we'll address them at the end of the webinar. So I want to start the presentation with 3 key take-home messages. One is that our findings suggest that overall water demand for California oil production has increased, and that's due to aging California oil fields use more fresh water and at the same time also generate more produced water that goes into evaporation ponds and surface water. That would be the first part of our key research finding. The second part is that the total transportation energy use and petroleum consumption will decrease if we are to achieve our 2050 climate goals set in California. The third point is related to the second, is that a climate policy that cuts transportation emissions will also at the same time reduce our state's demand for fresh water. But our demand for produced water could potentially increase quite dramatically, and our current infrastructure is not at the scale to handle that increased demand. Therefore, proactive planning will be needed in maximizing the utilization of non-freshwater sources. That's kind of the third key point that we want to raise in this research finding. So the next slide, this is the slide that just shows that in the projected increase in groundwater stress in California due to climate change, looking at compared 2005 level and the research finding from researchers projected in 2025 under climate change scenario. But as everybody is probably aware that California is currently in serious drought, so we essentially fast forward 10 years that we're currently under serious drought conditions. So water issue is a very important issue in California. Slide 6 shows that the scenarios that we're using for this analysis. On the left-hand side shows the reference scenario that we call reference scenario is basically a scenario that would meet the 2020 climate target, which is to achieve emission at 1990 level by 2020. And on the right-hand side is what we call deep greenhouse gas emission reduction scenario, which is a scenario that we will achieve our 2050 target, that is to achieve 80% emission reduction by 2050, 80% emission reduction from the 1990 level. And the scenarios are generated by our California Times model, which is an energy economic model that optimizes between 2010 and 2050. And so as you can see from this slide, that transportation emissions contribute to the largest share of emission in California. And our analysis will focus primarily on 2030 analysis, and so the white lines in both figures basically show what the emission in 2030 look like in both scenarios. The next slide shows the projected transportation fuel use in these two scenarios, the reference scenario and deep greenhouse gas emission scenario, emission reduction scenario compared to today's level. The total transportation energy use will be the lowest, and the petroleum use will also be the lowest in the deep greenhouse gas emission reduction scenario. Electricity that goes to the transportation sector as well as total electricity generation will be the highest in the deep greenhouse gas emission scenario, because we will, in that scenario, we will be increasingly relying on low carbon or even carbon negative electricity to meet our emission reduction target. In our water use analysis, we look at different sources of water as well as different disposition of the water. In terms of the sources, for each energy pathway, we look at potential existing and potential sources for water use, including fresh water, as well as several categories of non-fresh water that can come from wastewater, recycled water or degraded water, as well as produced water that's generated from oil production and oil fuels. And they all have various different definitions, and we try to the extent then possible define them as clearly as possible in the report. In terms of disposition, we also try to characterize where water goes at the end of the lifetime. So, for example, oil and gas production, they can go to evaporation pan or subsurface injections and so on and so forth. In terms of the biofuel, since it's an extremely complicated question, so we won't talk about biofuel water use in this particular webinar. We will discuss them in an upcoming webinar to be scheduled. And the only point I want to mention is that unlike most biofuel water use analysis that exists in the literature, our biofuel water use analysis will combine with the land use analysis. And so the story for biofuel water use is really a story about biofuel, the land use changes associated with biofuel policy. So that would mean that water use impact is an integral part of land use change that includes displacement effect, means crop substitution, land use expansion, land use intensification, as well as water management strategies. And with that, I'm going to hand the slides over to Jacob, who will give you an overview about the scenarios.
Thanks, Sonia. Sonia has already touched on a lot of the points that I'm going to cover here at the beginning. So as she mentioned, we use the outputs of the CA Times model, which is a cost minimization model with detailed economic and technical specifications for energy supply technology. And we use that to generate the portfolio of energy supplies serving California's transport energy needs. Our entire analysis is a consumption-based framework. So we looked into the energy and water needed to supply California's transport energy consumption. As Sonia mentioned, this gives us a different framework from if we had looked at production. We then broke down the sources of energy using CEC and EIA projections of future oil development, and further assumed that 20% of California's electricity would be generated out of state in both projection scenarios. In this presentation, we're going to restrict our analysis to the water impacts of in-state oil production and refining and electricity generation. In terms of sources of energy for transportation, California will go from a split of 95% petroleum-based fuels in 2012 to around 78% oil-dependent transportation in 2030 in both the reference and deep greenhouse gas scenarios. The main difference in the transportation sector between the scenarios is in the total energy consumed in transport, which is about 12% higher in the reference case, and in the composition of those alternative fuel sources. So again, what you see here are the energy sources for transport in 2030 under both scenarios. And if you're interested in looking more deeply at the percentages in each scenario, you can take a closer look at the breakdown given in the pie charts by downloading the slides. They are, as mentioned, available online. Also, you'll notice that for both of the climate scenarios, we created a smart and a baseline water management scenario. In the smart water use scenarios, we adopted optimistic assumptions concerning water sourcing and water use technology. And in the baseline water management scenarios, we simply extrapolated current water use trends based on state regulations for water technologies, water sourcing, and water disposal or FATE.
Hi, I'm Kate, and I'll talk a little bit about oil production. So first I'll talk about the methods of oil production, or the types, and then the way that water is used and disposed of in oil production, and then a little bit about the historical trends that we use to predict future use, and how they differ by the type of oil production. So first, going through the types of oil production, the first is primary, where you're using the natural pressure of the reservoir to bring oil up to the surface. At this point, this is pretty much just offshore in California. The second is secondary, which is when you begin to inject more water, or water flooding here in California to bring the oil up. And then the third type is tertiary recovery or enhanced oil recovery, when you begin to inject steam or chemical agents. In California, this is termed steam flooding or cyclic steam, which is also called the huff and puff method. So the way that water is used and disposed of, you're typically injecting water into an oil field and then bringing up the water-oil mixture from water in the formation as well, and thus generating produced water once that's separated from the oil. And the so-called produced water is either re-injected for additional recovery or discharged to evaporation ponds or subsurface wells, or surface disposal, which can include beneficial uses such as agriculture. So a little bit about California oil production history by the types that I mentioned earlier. Here we've got the secondary production on the bottom, which has remained relatively constant. Tertiary production, which has increased over the time period we're looking at, 99 to 2012. And then mixed production, which is a combination of secondary and tertiary, which has also decreased in favor of tertiary. And as you can see, California oil and gas production have been declining. They've actually been declining since the mid-'80s due to the aging oil fields, and you can really see that trend here. This is sort of a contrast. The oil produced, which I mentioned earlier, is in red and on the right axis, and then the water used has been increasing pretty rapidly while the oil produced has been decreasing. So this is actually broken out by the types of water we mentioned earlier. Other water, which is non-specified, produced water, which is coming from these oil and gas wells, and then the fresh water on top, which has also been increasing on the time period. So this leads to a total increasing water intensity from 99 to 2012. Here we have the water intensity, total water use intensity by the type of oil production, secondary, tertiary, mixed, and total. And this is broken out by the types of water, fresh, produced, waste, and other, and then also with the 95th percentile field as well out on that axis. So something to sort of look at here, you're really seeing the trend pretty markedly. Produced water use intensity is also increasing, has doubled almost from about 7 liters per liter or gallons per gallon to 15 down in the total here. You can see we've also got this broken out by the type of disposal or the water FATE. So green is going to subsurface wells, purple is going to sewer, blue is going to surface water, and then the orange is going to evaporation ponds. So you can see that increasing as well. And the evaporation ponds, the total amount spent has increased from 63 billion liters in '99 to 97 billion liters in 2012. And the water disposal to surface has also about doubled in the time period we're looking at. So evaporation ponds pose pretty big environmental problems. These are primarily unlined, so you can have leakage. There are off-gassing problems with volatile organic compounds, and then there's also an issue of wildlife mortality for migratory birds. This is the net use of water intensity of oil production in California, so sort of the new water that's coming in, and you can see that this is also increasing. It's increased from about 2.2 liters per liter to almost 3 liters per liter in the time period we're looking at, and the freshwater intensity use has doubled in that time period, which I think is pretty interesting. The total freshwater use was 3.8 billion gallons, or 14 billion liters, and the total produced water use was 54 billion gallons in 2012. So big produced water to get rid of, essentially. And I'll talk a little bit about the spatial distribution of the water injected and produced. This is a map of, on the right, the produced water disposal, and on the left, the water injection by water source. So you can see where this is all occurring in California. It's primarily in 4 or 5 counties, which all have high agricultural water use. Kern County specifically, where the big giant oil fields are. And then finally, I'll talk a little bit about hydraulic fracturing in California. Hydraulic fracturing has been used for a while, but we have about 2 years of data at this point. It's principally used to ensure that conventional wells attain maximum production, and it's generally vertical wells as opposed to horizontal, which are used in a lot of other places. The well age ranges from about 1 to 54 years, and hydraulic fracturing produced 1% of the oil that was produced in 2012. So here's a comparison of the water intensities, total water intensities for hydraulic fracturing versus conventional. You can see that hydraulic fracturing looks much lower than total conventional in the mean and median. However, only about 2% of the water injected for hydraulic fracturing was recorded as produced water or recycled water. So it may actually be that the net water use is relatively similar. And the majority of the water that is produced from hydraulic fracturing wells is going to either evaporation or water disposal wells as well, which could create problems with induced seismicity.
Switching gears now to electricity. This table shows the electricity generation portfolios for in-state electricity generation in the reference and deep greenhouse gas scenarios in 2030. In the CA time scenarios that we used, we assumed that nuclear power would be phased out in California and that CCS would not become viable for whatever reasons, political, technical, or economic. So you can see that the total generation in gigawatt hours increases only slightly in the reference scenario, whereas it increases by more than 30% under the deep greenhouse gas scenario as the energy supply electrifies, as Sonia mentioned. The deep greenhouse gas scenario generates additional electricity compared with the reference scenario, and it's primarily relying on technologies that consume little or no fresh water, technologies like tidal, solar, PV, and wind power. There's also an increase in the deep greenhouse gas scenario in generation by natural gas combined cycle plants, which do require more water per megawatt hour than the renewables that I've just mentioned. The other notable difference between the two policy scenarios is that in the reference scenario, you see that you generate about twice as much power using geothermal resources. And geothermal resources, binary and flash plants, could have a wide range of water use intensities depending on the cooling system and technology, but many of the most economically viable geothermal technologies consume substantially more water than even thermoelectric power generation. So we calculate the total water requirements for generating total electricity, the total energy coming from electricity by technology. Because California has quite strict laws on using fresh water for electricity generation, we project that fresh water use is cut roughly in half by 2030 in all scenarios, as a result of just phasing out plants that rely on fresh water. The graph shows only consumptive water use and not withdrawals here, since due to the phase out of plants using once-through cooling and the increase in plants using wet, hybrid, or dry cooling in California, by 2030, effectively all water withdrawn is also consumed. The state water resource control boards have a ranking of priority for water sources for electricity. It's a rather complicated split among many different kinds of water, but here we've categorized that split into simply recycled and degraded water. And you see kind of the water consumed in each of the 4 scenarios. In the baseline water use scenarios, we assumed that 75% of the new plants would use wet or recirculating cooling and 25% dry cooling. And in the smart water management scenarios, we assumed that there was an equal split, 3-way split among wet, hybrid, and dry cooling. So here you see the projections for total freshwater consumption for producing oil in the yellow and refining it in the brown and generating electricity in blue. For oil and refining, we simply assumed in the smart water management scenario that roughly half of the freshwater requirements could be substituted by alternative water sources, namely recycled water or through reinjection of produced water. So you see that the total freshwater requirements can go from just over 100 billion liters in the base year to about 70 billion in the baseline climate scenario for a 28% reduction in freshwater use. And under the deep greenhouse gas smart water use management scenario, which achieves the greatest reduction in freshwater use, California could even realize a 60% reduction. Now if we consider both fresh and non-freshwater use, the story is somewhat more complicated. This graph shows the base fresh and non-fresh water use on the left, the 2 bars on the left, as well as what you could think of as the 2 bounding scenarios. The scenario that uses the most water being the reference scenario with baseline water management assumptions, and the greenhouse gas smart scenario, that is the smart water management, which uses the least fresh water. So the total water use, that is fresh water plus all other water types, recycled, waste, degraded water, consumed in producing and refining oil and in generating electricity, actually increases in all of the scenarios except for the deep greenhouse gas scenario, that is when California meets its 2050 climate targets, and smart water management scenario. Here we take one last closer look at that optimistic future under which California meets its 2050 goals and manages water smartly, and what it might look like. The top 2 maps show the base year water consumed by water type. The colors indicate water type. And the maps on the left use a log scale, which essentially lets you see across orders of magnitude. You can think of it as it lets you visualize both the ants and the elephants, that is very low water consumption and very high water consumption in terms, The map on the right uses a linear scale that we're all pretty used to, so 10 billion gallons of consumed water shows up as a circle with twice the radius of 5 billion gallons of water. Without getting too much into the detail, and you can download the slides and take a closer look, the maps on the left show the reduction in freshwater use and the substitution of recycled instead of freshwater for electricity generation throughout the state. And the maps on the right, in those maps we can no longer see the water consumed by electricity generation except for in a few spots where it's using recycled water. But instead we do see modest but perceptible reduction in produced water use and in water consumed for producing and refining oil. So this analysis that we've conducted can serve as a foundation for 2 prongs of potential further investigation. First, it serves to identify potential hotspots in the state, regions where energy supply chains may exacerbate water scarcity or contribute to water resource scarcity and water quality impacts. We can identify certain counties or even certain locations where that might happen. And this can become the basis for detailed case studies which might incorporate economic, hydrologic, and even political and social dimensions. Second, by building upon the research of the state water regulations for oil supply chains and electricity generation, we can incorporate economic and energy costs of water treatment and cooling systems into the TA times model, thereby increasing the realism and fidelity of the model and hopefully providing more accurate predictions. So thanks for your attention, and if you've got any questions or ideas, we'd be happy to entertain them. And again, thank you to the California Energy Commission for funding this study.
Right, thanks a lot. A great presentation, a lot of information. Just to remind the folks on the phone that if you do have a question, please go ahead and type it into the chat box on the lower left hand of your browser. The ReadyTalk program allows you to send a message or a question to us. We will be doing these questions non-attributed, so we're just going to be asking them as they come in. We may combine a few questions depending on how many we get or if they're sort of thematically similar. If for some reason you don't get a chance to have your question answered, either because we run out of time, we will be available. You can email us or contact the researchers to do so. So we are getting some questions coming in here, and the first one is about agricultural water use, and I guess the question is, although it wasn't explicitly addressed in this webinar, do you have a sense of the scale of the ag water use relative to transportation and energy use? And I'll turn it over to you, Jacob.
So yeah, in the report that we'll be releasing soon for the CEC, we contextualize the water consumption for all of these energy supply chains by looking at what proportion that consumption represents relative to total 2005 county level withdrawals as given by the USGS. And what we find is that in the base year, if you sum up the water consumption across all of these energy supply chains and compare it to water withdrawals, and again, it's not a total apples-to-apples comparison because we're looking at consumption and withdrawals, water could then get back into the water table or run off back into surface water flows, surface water bodies. But we find that it's actually a very small percentage in most counties, between less than 1% of the water use, water consumption is going to these energy supply chains in most counties in the base year, but up to 7% in certain counties, and that's mostly due to electricity. And then if you fast forward to our projections, in certain counties there's between kind of no change or even a reduction in water use, but in certain counties there may be a threefold increase. And a threefold increase over 7%, it just so happens that it is in some of those counties where it already represented a substantial percent of water use, is significant. And so those are some of the hot spots that we've identified.
Great. So the next question is sort of somewhat a methodological question, and it's about the oil produced as assumed in the model. Is that all being used in California?
And the answer to that is yes. The short answer is yes. California uses or produces 37% of the oil that it uses in total. So yes, we do assume that all of California oil is consumed in California.
Okay, great. Yeah, so this is sort of a consumption-based one of the things that I think you mentioned early on as well.
I think it's a little bit different. It is, at least today, all of the oil produced in California is consumed in California.
Right. And in this model, basically, you're still sort of projecting the future, only looking at that which is used in the state.
Right. We kind of say if our oil demand is reduced, how would that reduce the production? Of course, there's the difference between consumption and production possible in the future.
So I'm going to jump down here, and there's a question about sort of trying to sort of interpret the scenarios. So it says, it's not clear to me whether or not the deep GHG will require more or less water, and why. What are the primary sort of factors that contribute to that? And I know there's a difference between the different types we've talked about. Maybe just focus on freshwater, which I know is a big issue. So the question is whether or not the deep GHG requires more or less freshwater and why. Just to kind of summarize.
So because you're consuming less energy, particularly less oil, you do see a substantial reduction in freshwater use going to oil production, that is both for producing oil and refining it. In terms of electricity, you're actually generating more electricity, right? But the scenarios that we've used show this shift from very water-intensive geothermal electricity production to technologies like solar, PV, and tidal that have, you can't say no net consumptive water use, but almost consume no water, especially in the operations. So there again, by reducing our emissions and our consumption of petroleum and electrifying across all sectors, you're reducing freshwater use in the deep greenhouse gas scenario.
So at the same time, the only additional point I would point out is that at the same time, California has very aggressive water policy of phasing out once through cooling technology and encourage the adoption of wet or hybrid technology, and both those technology will significantly reduce water consumption.
Great. So we have a couple different questions here that relate to sort of state regulation, and I know that's not your area of specialty or expertise, but if you have any sort of thoughts on maybe, given the results, sort of how you might advise or recommend the state. So I'll just read the two questions. It's, how do you anticipate this information being incorporated into existing and updated water plans, groundwater management plans that are going to be required? And then what might be the impact if groundwater use becomes regulated or more regulated by the state? And again, you can sort of pass on that if you don't have a specific insight on that, but if you have anything that comes out of the research.
Right. I think my preference would be to pass on, because it's really not, we kind of finish our first stage of research that trying to understand the impact. And we know that in California's 2030 scoping plan, water management is going to be a hugely important topic. So we kind of like finish our first step, and we look forward to interact with state regulators and stakeholders to discuss how useful this research will help to inform the future planning. And I think one thing we found in our research is that it seems to suggest that the infrastructure for you to use more recycled water or degraded water need to be significantly expanded. And when we look at the state's goal for state target for use of recycling degraded water versus the current rate of expansion, there's a huge discrepancy. So I think that would be a future area of focus for state regulators.
Great. And then I just have a comment here that's related to these questions, which is that with respect to state policy, the California Energy Commission has established a policy of no freshwater use for new power plants. And so that also is one thing that's already sort of contributing to, I think, some of the assumptions that go into these scenarios. And I guess I would just have another comment, which is, part of the interest of the Policy Institute in partnering on this project and this webinar is looking for those opportunities where this information can be plugged into the policy process. And so these are sort of the outputs of this work. If folks have ideas of where this might feed into ongoing deliberative efforts at either the agency or legislative level, we'd love to have that conversation. So I think one question here about the impact of the drought on water use for transportation energy needs. And I guess maybe I might expand, if you have thoughts on that specific question, but maybe I'll expand it a bit, which is the extent to which we understand the changing climate in California having impact on either overall or specifically transportation energy needs. Any thoughts on that?
Well, under most projections, water is going to become more scarce as a result of climate change, and that will restrict the supply and kind of tighten the screws. And just about all I have to say.
Okay. Good point. Let's see. Looking for others. Okay.
Isn't that all the questions we have?
Well, and I have a couple here in my pocket, but I do want to encourage folks, again, just to remind people, if you do have a question, feel free to type it into the chat box in the lower left-hand of the corner. We'll be taking those for the next 15 minutes or so. If you have a question on a particular slide, feel free to identify that in your question, and we can go back to that slide. And then if you haven't had a chance already to download the slides for your own reference, please feel free to go to our website, policyinstitute.ucdavis.edu, and do so. So my question is that you've got a certain set of assumptions about the changing composition, and I'll just, for electricity, you've got sort of a scenario there that assumes a certain future generation mix. Can you maybe say a little bit more about the sensitivity of the results to that chosen generation mix and what might differ if certain technologies went out over others?
Sure. And so the projected electricity generation in California is really taken from the modeling result from the CA times model, as I mentioned, and we 2 months ago did a webinar at California Air Resources Board to present our results from the CA times model. In the presentation, in the report, we generated about 10 plus scenarios to look at possible future of electricity generation mix, as well as overall state system use by 2050. And so it's really, as everybody knows, it's really difficult, if it's not impossible, to project future. So what we can do is just to do a scenario-based approach to look at, if we change assumptions in terms of the cost or technology characterization, how would the future electricity generation grid would change, as well as different climate policies would have an impact as well, not only in-state generation but also imports and exports. And there are also certain assumptions that we have to make in terms of, political will, or in terms of the preferences within the state. So, for example, nuclear and CCS is something that may have additional factors that you need to take into account beyond just the cost and technology performance. So, for those technologies, we simply assume whether they will, in some scenarios, we assume they won't come into play in our future generation.
Great. So we have another question coming in here. So you had talked about the hydraulic fracturing, and if I understood correctly, you were mostly talking about sort of vertical fracturing. So there is interest, of course, in the Monterey Shale, which might require some horizontal drilling and fracturing. Do you have a sense of how that might impact the results, or what the assumptions would be about different types of water use?
That's an interesting question. We just saw that the Monterey Shale had been sort of downgraded on what was technically recoverable. So I think it was about a percent. So typically horizontal drilling is more water intensive because you've got more contact, and the wells are much longer essentially. So what horizontal drilling is occurring in California right now is slightly more water intensive on a gallon per gallon basis, but not much. So I guess that's my best answer to that question.
Jacob actually did a very detailed review of looking at the water use intensity for shale gas production across the U.S. And what we can say so far is there's very little knowledge about how California shale is different. We know there, in terms of geology and the composition, California shale is very different from Balkan or other shale formation. So we decided we are not going to take the water use intensity that we found in other states and directly apply to California. So it's a huge unknown for industry and for us as well. So I would just probably leave at that. And we also know that in a shale, in producing shale gas, you need not just water, but also use a bunch of chemicals such as acid injection. So I think that's a future area of research for us.
Great. So there's I guess a comment here, and if you have sort of a response to it, it says that I guess wondering why the key conclusion slide that referenced oil production, that produced water is disposed of via two routes, either ponded or into surface water. Later, the slide correctly includes reinjection as a route. So maybe you want to talk about that in terms of, is that, yeah.
Yeah, so I will clarify. I did realize kind of halfway through the presentation we might use the terminology a little bit differently. That caused the confusion. The produced water, as you know, we produce much more, greater quantities of the water than we injected, and most of this position of produced water actually is being re-injected, as we show in the total water use slide. Sorry, I lost the control.
Oh, no, go ahead.
But, so majority of the produced water is re-injected, but when we look at the net basis, means that what's left after you re-inject water for more oil production, we just look at where does those water go, and like we said, they either go to subsurf, they either go to evaporation pond, or they get discharged into surface water, as well as a few unknowns that source disposition or unidentified. So the net water use intensity that we show essentially take into account, basically subtract the reinjection portion.
Great. Okay. So again, folks have questions, feel free to type them into the chat box. And just to let folks know, we're doing that for a couple of reasons. One is that it makes it easier to record the webinar, also allows for non-attributed questions, and given the number of folks we have online, it's an easier way to manage the Q&A. We have another, and then also just to remind people to make sure to sign up for our listserv for future webinars as well. I guess it's a question about just sort of, recent reports coming out, including from the California Council on Science and Technology, about fracking or the potential for such in California, whether or not we're sort of seeing any sort of new thinking on water use, and how that might factor into the research current, ongoing, or future.
Yeah, thanks for mentioning the CCST report. Maybe we can post that report on the website. But it's definitely a very good study and a great resource for us. And so I would encourage people who are interested in the CCS report, looking at fracking water use in California, and to take a look.
Great. So also kind of looking forward here a little bit, you had mentioned the fact that we will be having a study specifically on biofuel. Do you have a sense of sort of when that might be available? Any sort of teaser on what it might say, so that people tune in for the future webinar?
Yeah, we're planning on holding a webinar on the biofuel water use impacts, which looks at a national scope, and as Sonia mentioned, it also incorporates land use change considerations, and we use a crop water model, an agronomic model, to look at changes among scenarios in crop water use, things like transpiration, evaporation, runoff, groundwater infiltration, and we'll be holding that webinar in late November.
Right, and it's looking at the interaction of biofuel with conventional crop production across how many crops?
Roughly 16 of the major economic crops across the country.
Right. So again, I think at a very high level, the water story is very much, like I said earlier, it's very much the story about changes in land use as well as water practices. And we're looking at a net impact.
Great. Another question, maybe just to explore a little bit more on some of your policy implications. So one of the, I think, interesting parts of this modeling effort is that it has spatial resolution. So it's not just about sort of general parameters associated with different types of production technologies, but you're actually looking at where these things are likely to occur across the state. Can you maybe say a little bit more about that, and particularly as it relates to this concept of a hotspot analysis, which I think is an intriguing term?
So I guess in contrast to analyses of greenhouse gas impacts or projections of greenhouse gas emissions, water matters. It matters quite a bit where the water is being used and when it's being used. So water use is quite a bit more complicated than greenhouse gas emissions in the sense that water quality is a consideration. What kinds of use water can be used for depends on its quality. And again, the availability is dependent on both space and time. It has both spatial and temporal aspects. So when you do an analysis of water use, you do want to try to identify what kind of water is being used, when it's being used, and where exactly it's being used. Of course, when you're doing projections, you run into limitations of kind of the resolution that you can justifiably analyze water use across all three of these dimensions. But it's really important to try to capture that spatial element.
Great. And then I guess maybe also just in terms of this type of modeling, so in as much as you have both the consumptive patterns and spatial resolution on the electricity side, kind of looking forward, and even this is represented through the work that you've done on the CA Times, our energy system's going to transition not just in the transportation sector, but across sort of all sectors of the economy if we hit the long-term climate goals. Maybe a question is this type of modeling capable of looking across all those different sectors? Are there any limitations? And again, do you have any plans to do that in your future work?
Right. So, in this analysis, we cover total electricity generation and as well as transportation energy. So that pretty much covers all sectors, because commercial and industrial and residential sectors primarily use electricity as well as imported natural gas. So this analysis pretty much covers almost most of the energy pathways production within states. Looking forward, sorry, I'm trying to think about what are the other parts of the question I haven't answered.
So maybe just you talked a little bit about some of your future research direction, but do you have other thoughts about where you might take this?
Right. So one thing we haven't looked at, I think there are two primary areas we haven't looked at, or I can say three. One is that we really haven't linked back the reduced consumption of water with reduced energy use. As we say earlier that, or in our teaser, that California water sector is very water intensive. So to the extent we can reduce water use, we can also reduce energy consumption. And this is the part we haven't looked at. The second part of future research that we can look at more closely is the cost associated with using more recycled water, more degraded water. We made very heroic and simple assumptions about water smart strategies. In this analysis, we haven't looked at the cost aspect at all. And of course, that's a very important issue to consider in terms of cost and how do we expand the infrastructure to accommodate future demand for degraded and produced water, degraded and wastewater and recycled water. So I think that those would be the two areas I want to point out.
Great. Okay, I think we're coming here to the end. I don't see any other questions coming in on the chat box. If you're inclined in the next minute or so, if you want to type in one last question, we can probably get to it. But in the meantime, I want to thank our team here for the great work and for providing the information through this webinar. Just to remind folks again that this is going to be available, archived on our website. I also want to encourage people, if you haven't already signed up to our distribution list, to get notifications about future webinars on related topics, including the one on biofuel, which will be coming soon. And we'll have many others on other topics of interest as well. Again, this is Anthony Eggert with the UC Davis Policy Institute. Actually, we do have, one last question here, just under the wire, and it's specific to a slide here on slide 21. It's the question about the implications of sort of this water intensity. It says, does the table imply that 3 gallons of water are required to produce 1 gallon of oil under conventional methods? And then what's the difference between this and the net water intensity on slide 19?
Let me go back to 19. Right, so yes, so the short answer to your question is yes, it does imply that after you take into account the re-injected produced water, the net water intensity is about 3 gallons of water per gallons of oil produced. And in looking at slide 19, you basically, on the right-hand side, you are looking at the net water injection after you take into account recycling and so on and so forth. On the left-hand side, you see brown bars that represent the net water produced. And so we say, if you look at the last bullet, that's when I realized that we say total produced water used. It's actually total produced water produced. So on average, we're producing about 8 gallons of water, wastewater, per gallons of oil produced. So that's how you read the slide and scale. I want to point out maybe a very, very minor point that we see actually a huge improvement in more use of recycled and degraded water in the secondary recovery. But because of the nature of tertiary recovery methods, as we point out that there's increasing tertiary recovery because the wells are getting older, you actually need higher water quality requirement for tertiary recovery. So it does tertiary recovery does require more fresh water use consumption. So that's kind of the last point I want to point out. Do you want to add anything, Kate?
Just that the produced water produced here, the 8 is water that is not re-injected.
Yeah. Exactly.
Yeah.
Great. And then maybe even just in the last minute, any sort of final thoughts on sort of take-home? Okay, I think, again, great job. So the team here, Sonia Ye, Jacob Teeter, and Kate Tiedemann, thank you for your presentations. Also, Gauri Shankar Mishra is a team member to this effort. I want to thank the Institute of Transportation Studies as our partner through this effort, and of course, thank the Energy Commission again for their funding of this good research. Again, I'm Anthony Eggert with the UC Davis Policy Institute. Thanks for tuning in, and we hope to see you and hear you on future webinars. Thanks.
Thank you.
Thanks.